All right, so let's switch here. So in the next 20 minutes, I will go back to talk about the AVR processor. So as you can notice that I try to structure the lectures. First half or 2/3 of the lecture, we talk about some of the topics from the textbook, and then the remaining 1/3 of the lecture, I want to talk about the actual processors and not how you use the Arduino IDE environment, but we want to go at the more detailed look into the processor, how it's structured, and how the registers are supposed to be programmed and to support various functions. In the last 2 weeks, 2 times that we talked about the I/O, we talked about the timer. Today we want to look at the interrupts. We're already familiar with the concept of interrupts. Just to do a quick review, an interrupt is an event that disrupts the normal flow of the program execution. In embedded systems, interrupts are the rule. This is not an exaggeration, because in the embedded world, in cyber physical systems, you have to deal with a lot of events, a lot of triggers from the sensors, from your, and you want to be able to respond to these asynchronous events. So interrupts are very important. An interrupt may be caused by hardware, for example, by rising or falling edge on a pin or a expired timer. An interrupt can also come from software. You can write to an output port of a pin that triggers the interrupt option upon a rising or falling edge. And we'll see an example of that. For the AVR processor, they support a variety of events that can trigger an interrupt, including reset. If it's a power reset button, watchdog timer, that will trigger a reset interrupt. INT refers to external interrupt events on several pins, PD2 and PD3. And you have this PCInt. PCInt, those are also external pin change interrupts. But as we'll see later that these interrupts are not specific to a particular pin. Instead, it's all the pins for a particular port. So you have to have additional code to check which exact pin caused the interrupt. Timer also can generate interrupt that will indicating the time counter expire or reach to a certain threshold. And the UART or USCRT serial communication events also can generate interrupt when data arrives or your transmit buffer is empty. You can put this UART in the interrupt mode to operate that way. Analog digital conversion can also generate an interrupt when the conversion is completed. When interrupt occurs, this is how the processor will respond. First, the processor will identify the cause of the interrupt. Then it will redirect the control from the current running program to a predefined flash memory address in the interrupt vector, which contains a jump instruction to the interrupt service routine, or interrupt handler, sometimes called. So what that means is, if you look at the table on the slide, this is for the AVR processor. We have an interrupt vector table. In this table, there are interrupt numbers, numbered from 1, 2, 3, up to 10. And the addresses corresponding to these interrupt numbers are all set. And you can see the first interrupt, reset interrupt, corresponding to address 0000, and then the second interrupt INT0 that corresponds to address 0004. So every interrupt type corresponds to a address, and these addresses are 4 bytes apart. And that gives you the possibility to put in the program memory some instructions. And in fact, you will need to put a jump instruction there using these 4 bytes. So let's say you have a reset interrupt. The processor will suspend what's currently executing. It will go to this address 0000. And this is the address in the program memory. And typically you will find a jump instruction at this memory location, and that jump instruction will take the processor to the interrupt service routine. So the target address of that jump instruction will take you to the actual interrupt service routine. Same thing for other interrupts. You will see that you have jump instruction at all these places, and the target of this jump will be to different interrupt service routine, obviously. After serving the interrupt, control is then returned to the interrupted program. So the processor will resume the main task that it was executing before the interrupt happens. The AVR hardware supports all these interrupt shown earlier, and it has a register called SREG. This is a control register, and bit 7 of that register is a global interrupt enable bit. Normally that bit is a 1, otherwise all the interrupts are ignored. AVR processor has a few instructions to enable or disable interrupt. SEI to set that bit to 1, that means to enable interrupts. CLI is to disable the interrupts. RETI is the last instruction in your interrupt service routine. So this will take the processor back to the main program that it was executing. When an interrupt occurs, it will clear the I bit of the SREG register. That is to disable further interrupts. So that will not allow nested interrupts, which can be very messy to deal with for this little process. You'll then push the program counter onto the stack, and that's the return address to help the processor get back to the main program. You then write the associated interrupt vector address to the PC. So if it is reset, then 0 will be put into the PC. If it is INT0, then 4 will be assigned to the program counter. That's how the processor will get to the interrupt service routine. When the interrupt service routine finishes, the last instruction will be a RETI, and that will let the AVR processor to pop the original PC program counter from the stack to the PC register, and it will then set the I bit to 1 to re-enable the interrupts. Okay, so we can use 2 specific pins to as an external interrupt, but in fact you can use all these pins as an interrupt, and these voltage change on the pins will trigger a pin change interrupt, or PCInt. Each pin has an interrupt number, PCInt0, PCInt23, but don't confuse this with the interrupt vector. These are the numbers that will be grouped to generate this PCInt interrupt. We'll see in the next slide. For example, this is the Uno board, and using ATmega AVR4528P processor, and this pin 12 is wired to the PB4, which is assigned to the PC in 4. Okay, so we mentioned earlier that these pin change interrupt are not individually recognized, in the sense that these from 0, 7, 8 to 14, 16, 23, all these pins, even though we can detect their pin change, but they will, they are grouped into ports. And so if you're talking about PC end 0 up to 7, that will correspond to this PCI 0 or pin change interrupt 0. So not every single pin mapped to a interrupt. It's a group of them mapped to one interrupt type. For example, this pin PB4 that corresponds to PC pin change interrupt 4. This will trigger pin change interrupt PCI 0. So if you look at this group, so all these 8 pins, any one of them, if there's a change, that will trigger this PCI 0 interrupt. That implies when you have this PCI 0 interrupt, you will need to check, which pin indeed generated. And let's use the mask. We can use hardware registers in the processor to control the pin change interrupts. We have PCI CR, this pin change interrupt control register. We have 3 enable bits. Now, interestingly, we have 3 types of pin change interrupt, and then we have 3 enable bits. Right? That's by design. It's designed for control these 3 types individually. If you read other microprocessor data sheet, you will always find these interesting matches, because the way they design these registers and control bits in these registers are to make sure that there are always some kind of mapping. You can control one type of function or feature using 1 bit in the register. The other control register is the mask. In this example is pin change mask 0 is to mask out any of these 8 bits in this first group. You can see that's PC in 0, 1 up to 7. So that corresponds to all these 8 bits here. I should say 8 pins here. Okay, so we have an example to enable the pin change interrupt on this Uno pin 12. That corresponds to pin change INT4 as a part of the first group. Okay, so we know this first group corresponds to PCI 0. So we'll have to do something with this to enable this first group. So what we have to do is to assign 1 to this register. So that's what we do in the first step, assign 1 to this register. As a result, this bit will be a 1. That will enable this first group, the first group of pin change interrupt. The second step is to enable this pin change interrupt 4, which is one of these 8 pins in this group. So we'll set bit 4 of this mask, the pin change mask 0. We'll assign 10 hexadecimal to this register. So 0, 1, 2, 3, 4. So this is the 1. Okay, this bit location will be a 1, and all the rest are zeros. So we only consider this this pin, and we ignore the other 7 pins. Even they have any voltage change, will not they will not generate an interrupt. Only this bit will generate interrupt. And then eventually we'll enable the global interrupt. So we'll do SEI. That's one instruction to enable the interrupt. Any questions here?
So can you have more than one interrupt connected to the PCI 0?
Okay, good question. I think you're talking about this group. As we said earlier, that this group has 8 pins. And so any of these 8 pins, if there is a change in the voltage, this interrupt will be generated. If you enable more than one bit, let's say this, you have, let's say 1F, okay? So if we do 1F, that means we have 1 here, 1, 1, 1, 1. We have 5 of these pins are not masked. So we're gonna be allowing all these 5 pins to trigger this interrupt. It's possible, you can do that. So any pin, if there's change on any of these 5 pins, this PCI 0 will be triggered. Then it's your job to actually check the, each individual pins to see what changes that. So that will, that's possible. In some cases, you may want to do that, but some cases you don't want to do that. So that's the kind of the trade-off of using this pin change. They give you a lot of coverage on different pins, but still you need to either use mask or use your other instructions to check which pin has the change. Did this answer your question?
Yes.
Okay. All right, the next example is software interrupt. Software interrupt is to trigger a interrupt by using software instead of using actual voltage change on the pins. We can trigger a pin change interrupt by writing to the pin in software. This pin 11, we use this as example. This corresponds to PC pin change interrupt 3. That's PB3 for the actual pin. There's no external hardware required. You can keep the pin dangling, so not connected, and you should not connect it. And you can configure pin 11 for digital output. Remember in the first part when we talk about the GPIO on AVR, in order to make this pin as an output, we need to use this control register called DDR-B, and we choose 3. So this is the data direction register for port B at location 3. So that's the 4th bit because we're counting from 0. So we're going to set that to 1 to indicating that's an output. And then we will enable pin change interrupt on this pin 11. So that's PCINT 3. That's also part of the first group. So we'll, basically the earlier slide shows us how to do that. So that will enable the interrupt on that pin. But instead of relying on voltage change, we can use the software to write write to that pin by using the port B register output. And we can toggle the value on that pin. So if you write to 0, let's say if reset status is 0, and if you write 1, that's a pin change. If you write 1 again, it will not trigger interrupt. But if you write 0, that's a pin change, so that will trigger an interrupt. Okay, and there's a note for this kind of software interrupt. It's not available in the Arduino libraries. You need to write C or assembly doing bare metal programming. And we'll talk about bare metal programming in the next class. So far in what we have done in the labs, where you use Arduino IDE and the libraries to build different function blocks together, adding control flows, adding state machines. But it's also possible that you don't use all these IDE environment and the Arduino libraries. You can program by writing assembly or C language and operate these registers directly. And that's called bare metal programming. You don't use those libraries. Okay, next example is the timer interrupt. Here's a task. You want to start a timer that expires after 100 microseconds. Then increment a counter and restart timer unless the counter has reached the value 100. So essentially we want a timer that's 100 microseconds. What we want to do here is to find out how many cycles we will need to set on the timer. It's easy to calculate. If you have T as 100 microseconds and the clock frequency is, let's say this is, sorry, the clock time is 100 millisecond, and then the clock will be this 100. That's 1 over megahertz, and that will give you this 1600 cycles, assuming that it operates at 6.5 megahertz. And so this is the number of cycles we need to have the counter to count up. And then we need to choose a value in a counter register so that it will do this number of cycles. We'll count these number of cycles. We use these timer counter 2, and as part of it, this count register TCNT2 is an 8-bit counter. That means it can count up to 255. So from 0 to 255, and that's 256 cycles. So it's not possible to count up to 1600 cycles. So we need to do some scaling, and that's why we use this pre-scale factor. If we use 8, what we can do is we calculate 1600 divided by 8, so that's 200. That means if we use this TCNT2 as a counter, and with this pre-scaling of 8, we are talking about counting a value from 0 to 199, so 200 times, because each time represents 8 cycles. You can use larger ones, and so this value will be smaller, but if you use a smaller pre-scaler, that's preferred because that gives you smallest resolution. Because if you use 32, that means when the counter increased by 1, you are actually counting 32 cycles. For this case, maybe fine, but for, well, this case is not, let me see. So 16 divided by 32, yeah, there's some error would be generated. So it's better to use a smaller pre-scaler, so you have smaller resolution. So now we know that if we use pre-scaler 8, pre-scale 8, we need to set a counter to count up to 200 or 200 times. So it starts from 0, so we need to set the value as 199. For the counter interrupt, we will need to use a few registers. One is the output compare register that will set the upper bound the value that you want it reaches to before reset the counter. The equality comparator will compare the value you set in the register, and if they're equal, and it will trigger interrupt, and in a clock cycle after detecting there's a match, and that's the timer interrupt. Also, it offers a clear timer on compare match mode, so it will set that to 0 and start counting again. So this TCNT2 will do the counting, so from 0, 1, 2, 3, up to the value that you set in this OCR2A or OCR2B. To generate an interrupt, you also need to set a few bits for the mask. You need to set the configuration, this 2A, to indicating that we're going to be using this OCR2A as the upper bound for the counter. So a few lines of code will help us to accomplish what we wanted to do. We first select the counter mode. There's a control register you need to set, and then you set the prescale factor of 8. You can check the control register just to find out, okay, which bits are used to select prescale factor is it's the lowest 3 bits. And then you set the upper bound to be 199. This is because we want the counter to count 200 times, and it starts from 0, so up to 299 before it goes back to 0. It enables the output compare a match interrupt by using this mask, and initialize the counter to be 0, and then enable the global interrupt. And then you're all set. So, well, of course, you need to have an SR, interrupt service routine, for this particular interrupt. This is one of the interrupt vectors that you see in the table earlier. So that will help you do that. By the way, so this is comp A, so timer comp A, so that's this one. So your interrupt service routine, and so here is the address for this vector, and here you will find a jump instruction. You're jumping to the interrupt service routine that you define somewhere else in your program. Okay, so a summary, a few things that you need to do to for using the AVR interrupt. You want to keep the interrupt handler short. You want to just set a flag and do a lot of the other things in a main loop function based on the flag. And you want to save and store the as register in SR. That's default in C. You don't have to really save that register if you are programming in C. When handling interrupt, further interrupts are blocked, so there's no nested interrupts. If there are concurrent interrupts happening, the smallest number will have a higher priority. The CPU always finishes instruction before jumping to the SR. And CPU executes one loop instruction between handling pending interrupts. And the interrupt handling takes about 8 cycles. 1 cycle push to PC, 3 to jump, and another 4 to execute return I. You normally don't have to worry about this, especially when you're programming using C. But if you have very tightly controlled timing properties to match, then you may want also consider these overheads.